Hi, I am Varun Joshi and welcome to day 29 of our Certified Kubernetes Administrator 2025 course. In today's session, we are going to explore Kubernetes workloads like Daemonset, Job, and cron job. These powerful workload types are essential for managing background tasks, batch jobs, and scheduled tasks across your Kubernetes cluster. What you see on screen is a Kubernetes cluster. We have a control plane, a data plane. Control plane has a control plane node and that node is tainted. Then we have worker node 1, 2 and 3 in our data plane. On the left, you see there is a deployment YAML. This deployment YAML is creating two pods for us, and these two pods can be placed only on these three worker nodes because the control plane node, as we see, is tainted, and in my deployment I have not specified any tolerations. I also want you to understand that the taint that is applied onto the control plane node has an effect of no schedule. When you create this deployment and it reaches the stage where the scheduler has to decide where to place these pods, and what we saw in day 15, that scheduler has specific considerations before it assigns a node name to a pod, and those considerations are resource availability, taints and tolerations, affinity and anti-affinity rules. In our example, the scheduler decided to place these pods onto worker node 1 and worker node 2, one pod each. But I want you to understand, in case node 2 or node 3 both had enormous resource crunch and there were taints, node affinity also applied onto the pods, then both these pods could have been scheduled onto a single node itself. So scheduler does not guarantee equal distribution of workloads, and when it comes to deployments, we do not really care. We just want that our pods should be running. Kubernetes behind the scenes decides where to place these pods and ensure the desired number of pods are always running. But why are we discussing about these workloads? With deployments, we didn't care where our pods were placed, but I want you to imagine a scenario where I want to run one pod in every node. For example, if I had this replica count to 4, I would have wanted that 4 pods to run, one on this node, one on this, and one also in the control plane node. For use cases like that, we have something called Daemonset. But Varun, why would I want to run one pod in each node? You would want that because when we talk about logging, for example, you would want to collect logs from each worker node along with the control plane node, and in addition to that, there are several other use cases, for example monitoring, security, and we'll be discussing these in a few moments. But that is where Daemonset come into picture. Daemonset ensure that one pod is running in each available node. Now, whether we run that pod in control plane node or not is based on a few factors, and we'll see those factors as we move on with this lecture. What you see now is there is a kubeproxy pod running in all the nodes, and kubeproxy runs as a Daemonset. If you remember, in day 7 we learned that all the nodes also run a kubeproxy component, and if you see here, both worker node 1 and worker node 2 are running kubeproxy. Now, what was kubeproxy doing? Kubeproxy was doing service to pod networking, and it was load balancing. For example, if a front end pod wanted to speak with Redis backend, then kubeproxy was the one which was deciding which pod will be serving the traffic. Secondly, it was only forwarding the traffic to the healthy pods. For example, if node 2 had some problem, then kubeproxy ensured that only the healthy pods, for example in worker node 1, should be receiving that traffic. And lastly, when the front end pod sends a request, it sends the request to the IP address of the Redis service, not the IP address, it is the DNS name, and behind the scenes it is core DNS which will be doing the name resolution for you. Now when the pod would have the destination IP address of this Redis service, and it is the kubeproxy which changes the destination IP to the pod that will be serving the traffic. But why was kubeproxy running in all the nodes? We said that kubeproxy is the traffic director, hence we wanted kubeproxy to run on all the nodes. If I move back to day 29, you see that kubeproxy is running on all worker nodes, including the control plane node, which implies that the daemon set that deals with kubeproxy has a toleration, which is why the control plane node can also run kubeproxy. Now let's go to the terminal and see how the kubeproxy is working. So if I go here and I run kubectl get daemon set, ds is the short name for daemon set, and then I will write -n kube system because it is the kube system namespace where the kubeproxy runs. So I'll press enter and I'll see that there is a daemon set called kubeproxy, and the desired count for that is 3 and the current count is also 3. Why is this 3? Because if I run kubectl get nodes, I see there are 3 nodes, and in each node one kubeproxy would be running. If I would have had 4 nodes, then I would have 4 instances of kubeproxy. As and when the nodes are added and removed from the cluster, the daemon set pods are also added and removed. So if I run here kubectl get pods -n kube system and I add a -o void here, I get all the pods that are in the kube system namespace, and I've added -o void because I want to know the node name where these pods are running. So what I'll do is I'll grep for kubeproxy, and as soon as I do that, I see these 3 are the kubeproxy pod, and you see here in every worker node there is one kubeproxy running because kubeproxy is deployed as a daemon set. Now let's do one more thing. I'll again run that command. I'll run kubectl get daemon set ds -n kube system. The name of the daemon set is kubeproxy, and I want to see the YAML for that daemon set. What I want to show you is why the kubeproxy pod is also running in the control plane node. So if I press enter here now and I look at tolerations, you see here are the tolerations, and here we just see operator which says exists. So this implies I don't care what is the value of the taint, what is the key of the taint, and I don't even care what is the taint effect. I tolerate everything. So this toleration is a catch-all. It does not matter what the taint is, this pod will be tolerating all the taints. This implies that. Now we know why kubeproxy is also running on the control plane node. So let's go back to our diagrams now and let's see what is a daemon set. Ensures a specific pod runs on every node. This we have already seen. Auto manages pod creation deletion as nodes are added and removed. Do daemon sets run on control plane node? There is no straight answer for it, but it depends. So if you are using a managed cluster like Amazon EKS or Azure AKS, then you would see that the control plane is highly governed by the cloud provider itself. The cloud provider is the one who takes care of your control plane components. So when you deploy your own security agents or your monitoring agents, logging agents as a daemon set, then your control plane node will not be running them, but all your worker nodes will be running your daemon set pod. If I talk about self-managed cluster, that is where you are the one who is managing the control plane, then you would see that it depends on your specific requirement. Having said that, every time there is a taint on a control plane node which prohibits any workloads or any pods that you provision to be running onto the control plane node. If you want to run your daemon set onto your control plane node as well, then you would have to have the appropriate toleration. Like we saw, the kubeproxy daemon set has a toleration that allows any pods of this daemon set to run on the control plane node. And in the demo section, the daemon set we'll be using will also run on a control plane node. Next is commonly used for infrastructure components. Why are we saying that? Because see, we discussed the example of kubeproxy. We know kubeproxy acts as a traffic director, hence we want kubeproxy to be running on all the nodes. Similarly, if I talk about monitoring agent, I want the monitoring data from all the nodes along with the pods that are running onto that node. Hence, monitoring agents, logging agents are deployed as daemon sets. If I talk about network plugins, we have discussed about CNIs, and CNI plugins like Calico, Flannel, and even on cloud providers, AWS VPC CNI or Azure CNI, all these also run as daemon set. Then storage plugins, we have talked about storage plugins in detail, and we know that CSI plugins will add storage on all the nodes. So we would want the CSI plugins to be available in every node. Hence, storage plugins are a use case where we would use daemon sets. And if I talk about AWS EBS CSI or EFS CSI, they all use daemon sets. If you have any confusion pertaining to CSI, I would urge you to go through the storage section of this course. We have discussed CSI plugins and their different use cases in detail in that section. Now let's go to Visual Studio Code and start with our demo. I already have a pre-created ds.yaml, ds as in daemon set. So if I scroll at the top, let's first run our favorite command, that is kubectl API resources, and then I will grep -i ds daemon. Let's write daemon here, and I see that daemon sets, the short name is ds and the API version is apps/v1. They are namespaced, and then this is the kind daemon set with DNS uppercase. I'll go to my Visual Studio Code, and that is what we have written here. API version is this, kind is this with DNS uppercase. Then metadata section, we are naming this daemon set log collector because we are simulating a log collector in our Kubernetes cluster. So then we are specifying a namespace here. We have discussed about namespaces in detail in our day 14 lecture, and we understand that as a best practice, your applications should be segregated into different namespaces, not just applications. The segregation could be based on your department, project, environment. Hence, primary purpose of namespaces is to provide you proper segregation so that your workloads could be residing in your specified namespace. Now, this segregation is not just important from a logical perspective, from the perspective of segregating your workloads, but understand, if you want to delete any components pertaining to, for example, application 1, then you just delete the application namespace, and any Kubernetes objects that this application was using, for example, any deployments, roles, service accounts, network policies, anything that was namespace specific and this app was using, as soon as you delete the namespace, everything will be gone. So namespaces also helps you in keeping your cluster tidy. So let's go back to Visual Studio Code. Hence, when we talk about all these infrastructure components like your monitoring agents, logging agents, security agents, in those scenarios you will be deploying those onto their own namespace. So for example, in future, if you want to change your security tooling, then you just delete the namespace of your previous security tool and then you deploy your new tool in its own namespace. Hence, here we are saying the namespace for this daemon set would be logging-ns. And similarly, we saw when kubeproxy was deployed, kubeproxy is a system component which was deployed in its own namespace, kube system namespace. Kube system namespace is for your system level components. So let's go back here. So this deployment will be handling any pods that have app is equal to log collector label, and the daemon set also has app is equal to log collector label. So if I move down, I have specified a toleration here, and this toleration says I tolerate the taint on the control plane node. So if I go back to my terminal and if I run kubectl get nodes and then I run, let me zoom in a little, and then if I run kubectl describe nodes, and the node I want to describe is control plane node, and if I scroll up here, I see that there is a taint applied to it. The key of the taint is this, and I don't see a value associated with that key, and the effect of the taint is no schedule. And if you have any confusions pertaining to taints and tolerations, go and watch day 16. If I want to run a pod on this node, then that pod should have a matching toleration. So that is what we have added here. We are saying that as long as this key exists, then you can schedule this pod onto that node. So this pod is essentially tolerating the taint that is applied to the control plane node. Then I have a container. Container's name is log collector. Image is busybox. Command that we are running is simple. We are saying just echo collecting logs and then sleep for 30 seconds and done. We have also defined resource requests and limits, which is a critical part in production grade applications. You would always want requests and limits defined, because you do not want your application, or in this example your logging agent, to starve other applications or processes or microservices from their required resource usage. Hence, we are defining resource requests and limits. And if you have any confusions pertaining to requests and limits, go and watch day 19 of this course. Then we have a volume here. The volume type is host path. I want you to understand, here we are using a host path volume to simulate access to nodes var log. In production environments, logs would typically be shipped to a centralized file storage like EFS in Amazon, normal file storage, and object storage. It could be your Google Cloud Storage or Amazon S3 bucket or your Azure blobs, or it can also be streamed directly to tools like Elasticsearch, Loki, or a cloud native logging service like Amazon CloudWatch Logs. So here we are using host path, and then we are mounting that volume onto the mount path var/log in the pod. So let's go to the terminal and apply this manifest. So I am already in day 29. I'll now run kubectl apply -f ds.yaml. Oh, what does it say? It says namespace logging ns not found. So if the namespace is not there, this command will not automatically create the namespace for you. So let's create a namespace, kubectl create ns logging -ns. I'll press enter and it says that the namespace is created. I do not want it to spell like this. I want proper spelling, so I'll press enter now, and then I will delete the wrongly created namespace. Delete namespace, and the name is logg logging -ns. I'll remove this, and then now let's apply our YAML. kubectl apply -f ds.yaml. I'll press enter and it says log collector created. Now if I run kubectl get pods, I don't see anything because by default my commands are running in the default namespace of the current context. So what I'll now do is I'll run kubectl config get contexts. I'll press enter and it says your current context is kind MySecond cluster, and the cluster that you are dealing with is kind MySecond cluster, and the authentication information is also kind MySecond cluster. And if you have any confusions pertaining to these concepts, go and watch day 8 where we deployed the kind cluster and also discussed about Kubernetes contexts. And you can also refer day 14 where we discussed Kubernetes namespaces, and there also we discussed about Kubernetes context. So for now what I want to do is I want my current context to be running commands in the logging -ns namespace. So what I'll do is I'll write kubectl config set context, and I'll set the context for the current context to the namespace of my liking, which is logging -ns. I'll press enter, and whenever now I run kubectl get pods or any other command, that will run in logging namespace. So I'll press enter and I see there are 3 pods in this daemon set. Now I want you to understand one thing very clearly, that when we talk about daemon set YAML, you will not see anywhere we are defining any count, because we don't have to do that, as we know that daemon set pods will be running on every node in your cluster. Now control plane is an asterisk. If you add a toleration, it will also run in the control plane node. So if I go here, I see there are 3 pods running, and if I add a -o wide along and press enter, I see that each node is running 1 pod for this daemon set. And I can also run kubectl get ds to get details of this daemon set. I can also run a describe to describe this daemon set, and it will show you the details about it. Now let me see if I want to explain anything else when it comes to daemon sets. Oh, I think that's all I wanted to cover in daemon set. So let me clear my screen. I will write kubectl get daemon set. Now I could delete this daemon set separately, or what I can do is I can just delete the namespace. I'll run kubectl delete ns logging ns, and I press enter, and I see the namespace is deleted. Be very careful in production implementations when it comes to this command, because this will take away the soul of this namespace. It will delete everything that is inside it. So be extra cautious when you are using this command. I have committed this mistake in the past. We all have been guilty, so be extra careful with this. The namespace is now deleted. If I run kubectl get pods, you would see that my context, my current context, is still pointing to the namespace that does not exist. So let's just quickly change that. In the namespace section, I am saying that for the current context, you should set the namespace to default. And we know if you want to check your current context, you can run kubectl config get context. It will tell you what is your current context. So I hope you have understood daemon sets. They are important, and in production environments you would see them being used all the time. Let's move to the next section, and the next section is about job and cron job. Before I move forward, I want you to know one important thing. Job and cron job are not part of CK curriculum, but knowing these things exist will help you in production implementations, because you would see that job and cron job are always used. If you are here not just to clear the certification but to have real production grade knowledge, then I would suggest you stay with me and also see how job and cron job work. So let's get back to the topic. What is a job? And yeah, before we move forward, if you are new to this channel and if my content is helping you in any way, then I would urge you to like my videos, subscribe to my channel, and leave a comment, even if it is just a hi or a thank you note. It helps more than you think. So what is a job? Runs one-off tasks that start, complete, and exit. What is the difference, Varun? When we were dealing with deployments, we know that deployments usually run those tasks that are supposed to run continuously. For example, your web servers. You want your web servers to run 24/7. Hence, you would use a deployment to deploy your web servers. Or your API gateways. You would want them to run 24/7. Hence, you have deployments for that. But what about one-off tasks? For example, if I want to, let's say, ping 4.4.4, and if my container does that, my container's status is complete, and that is what I want. I don't want that to run 24/7. What if I want to copy a file from place A to place B? That is a one-off task. I don't want that pod to run 24/7. As soon as the file is copied, I want that pod to be in complete state and go away. Maybe I don't want it to stay in my cluster. So if you have these sort of tasks where you want to do one-off tasks, then you would use a job. And also cron job if you want to run something in schedule, and we will see cron job later in this section. Then we have creates one or more pods to run a task to completion. Now copying a file from one place to another is a very small task, but let's say you are dealing with gigabytes of data, then one pod might not be sufficient to do your job. In that scenario, you would want multiple pods to perform the copy of the file. Hence, you can create one or more pods for a job depending on your requirement. Retries automatically if a pod fails based on backoff policies. We'll see this in detail in our demo section, but for now, backoff policies will recreate the pod if the job fails. Commonly used for batch jobs, and batch jobs could be like what I said, copy one file from one place to another. It could be deleting temporary files. Then it is also used for migrations. Maybe you want to change the DB schema, then you can use job object. Then there are utilities like clean up temporary files, take backup. Then there are one-time reports. You want to, run some analysis, and then that job is complete. So you can use a job object for that. So if I go to terminal and I run kubectl API resources, and then I grep or job, you see cron jobs and jobs. So jobs are part of batch v1 API, and they are namespaced, and here you see a job. So both jobs and cron jobs are Kubernetes objects. So if I go to the Kubernetes documentation, and then if I search for cron jobs here, let's say, and I go to this section, you would see that under workload management, we have all these things, and most of these we have already discussed, excluding stateful sets. That will come later in the course. And these jobs and cron jobs are part of workload management. So let's go back to our diagrams, and then so we understand what a job is. So let's go to Visual Studio Code and do a demo for the same. So let's open job.yaml. Again, see, you do not have to memorize the YAML as long as you understand what these things 2. So if I want to check the YAML for something, you can even access these in the exam. So I go here, I click on jobs, and then I know what fields I have to use when it comes to job. So don't fuss about remembering these. You don't have to memorize these. So API version is batch v1. We just saw that using kubectl API resources, batch v1, and then the kind is job as expected. The name of this job, I'm naming it hello job. Spec, under the spec section, let's get to the meatier part now. It says TTL seconds after finished. It says once the job is complete. I'm not saying whether it completed successfully or it failed. I'm just saying when a job completes, remove that pod after 60 seconds. Because imagine you have hundreds of jobs running in your Kubernetes cluster, and once that job has done its job, you do not want to see so many pods in your cluster when you run kubectl get pods. You want your cluster to be tidy. So you use TTL seconds after finished so that any pods that have completed can be removed after 60 seconds from the cluster. But Varun, if something failed, wouldn't I want to troubleshoot that? If you remove that object from the cluster, then how will I troubleshoot? See, when you are dealing with production implementations, always you would be using a logging agent, and that logging agent will be running as daemon set, and your daemon set will be already collecting all the logs from all your pods, from your nodes. Hence, you will already have logs someplace in the centralized storage. Hence, you can feel free to clean your pods once the job is completed. Again, if you do not have a logging agent, you should first have a logging agent. If you don't have, then you can get rid of this timer. Then there are completions. What are completions? Think of completions as pod completions. What I am saying is this job is supposed to run 2 pods, and both those pods should have completed the job successfully for this job to succeed. Understand, if I am saying 2 here, this job has 2 pods, and if both these pods did the job perfectly, they completed the job successfully, only then the status of the job would be successful. If one pod out of these 2 pods was not able to finish the job, then the job status would be failed. But Varun, why will be 2 pods running a job? Why can't 1 pod run the job? Imagine you are, let's say, processing 10 GB of data. If you have 2 pods, then 1 pod can deal with the initial 5 GB and another pod can be dealing with the next 5 GB. It is all about load distribution. For example, why do deployments have multiple replicas? Because your application load warrants that much replicas. Hence, in job as well, if you are doing a strenuous task, then you would want multiple pods to be running at the same time. Let's talk about parallelism now. Parallelism says it is 2 here. It says I want you to run 2 pods at the same time. So 2 pods will be running concurrently. So in the completion section, we said I want 2 pods. In parallelism field, we are saying that I want both those 2 pods to run simultaneously. If this were 1 here, then that would imply first run 1 pod, let that pod complete its job, then run the second pod. So completions is defining how many pods I want, and parallelism is defining how many pods can run concurrently. So if you have this 1 here, then the pods will be running sequentially. For example, if I change this to 10 and I change this to 5, then I will have 2 pods running concurrently, but I want 10 pods. So first 2 pods, then 2 pods, then 2 pods, then 2 pods, then 2 pods. 5 times it will run, because 5 into 2 is 10, and that will be 10 pods in total. But only 2 pods are supposed to run concurrently. If I change this to 1, then all these 10 pods will be running in sequence. First one will start. Once that pod finishes its job, then the second, then third, fourth, and so on. So for this example, let's change this to 2. Let's change this to 2. Back off limit is defined as 4. So if a pod is not able to complete the job at once, it will be given a second chance, a third chance, and a fourth chance. If it fails the 5th time, then the job is deemed failed. So back off limit will recreate the pod. I'm choosing my words carefully here. It will recreate the pod. I'm not talking about containers here. I'm saying a new pod will be created, and we'll see why it matters in a little while. Then I have the template section. Template section has the spec. Then we have containers. We have seen that name of the container is hello. Image that we are using is busybox. Then the command that we are supplying is echo hello from the job, and then it will sleep for 10 seconds. The restart policy, this is an important field. When it comes to jobs, you can only have on failure or never. Always is not a policy that you would using for job, because you do not want to restart a container if it has already performed its job, if its status is complete. A key thing I want to mention here: if you have any confusion about restart policies, then please, this is an important lecture. I would suggest you go to day 22 and you check out restart policies, because it is imperative that you understand restart policies. And this lecture not only deals with restart policies, but important concepts like pod termination, pod life cycle, image pull policies, common command errors. So do visit this lecture. Now, what we said in this lecture, we said that when we talk about web servers continuously running tasks, then we want the restart policy to be always. But when it comes to job, we want the policy to be never or on failure. So let's go to Visual Studio Code and see why does it matter. When I talk about restart policy, understand that restart policy is something that is governed by the kubelet. So kubelet is responsible for restarting your containers if they fail when you have a restart policy of always. And on failure, if the container fails, then the kubelet will restart the container. Here we are restarting the containers, but when I talk about back off limit, here the job controller, we learned in our day 7 lecture that there is a controller manager. Controller manager is responsible to ensure that the desired state matches the current state. And then we said controller manager is an umbrella term. There are multiple controllers that work under this umbrella term. For example, if I run kubectl API resources, then you see these many objects can be created in Kubernetes, and most of these objects have a corresponding controller. So when I talk about jobs, jobs also have a job controller. So job controller is the one that ensures the pod is recreated based on the back off limit counter. Restart policy is kubelet and it will restart the container, but the back off limit will recreate the pod. So it won't be restarting the container inside the pod. It will be recreating the entire pod. So it will retry 4 times, and if the pod is not able to complete the job 4 times, it will deem the job as failed. This is an important concept, and whatever I taught here, you do not have to make notes for it, because if you go to the GitHub repository, it covers everything. Whatever we have discussed, it covers in detail. So be it your completions, parallelism, it covers everything. So let's go to Visual Studio Code and let's apply this. Let's go to the terminal. I'll clear my screen. I'll run kubectl apply -f job.yaml. I'll press enter and it says the job is created. I can run kubectl get job. It says that there is a hello job which is running. Completions is 0 of 2. There are no pods yet created. So if I run it again, it says 1 pod is created. If I run it again, it will say 2 pods are now created. Why are 2 pods created at once? Because if we go here, we have supplied completions as 2 and parallelism also as 2, which is why 2 pods are running concurrently. If I now run kubectl get pods, you see that both these pods are now completed, which is why the ready status is 0/1. After 60 seconds, both these pods will go away, because remember what we have specified, TTL's seconds after finish is 60 seconds. And now I can run kubectl describe job, and the name of the job is hello job. If I press enter, it will tell me all the things pertaining to this job. This says that job is completed, and you can scroll above and read this information further. Here you can see pod status is 2 succeeded. If I run kubectl get pods, I see there are no resources in this namespace, because both these pods finished their job and after 60 seconds they were removed from the etcd data store. I want to run it again, run this YAML again, so that we can watch it. I'll run kubectl apply -f job YAML, and then I'll run kubectl get pods -w. Now you see, now it is status is both are ready and it is running. And as soon as this will run this command, and then it will sleep for 10 seconds. So after 10 seconds, the pod will complete. And you see here, roughly after 10 seconds, the pod has the completed status, and use the ready counter also changed, because now the task is completed. I hope this is understood. I'll press Ctrl C to exit from here. I'll clear my screen. I will delete this job, kubectl delete job. The name of the job is hello job. I'll press enter and the job is deleted. If I run kubectl get pods, I see nothing is there in my default namespace. Let's now go back to the diagrams and discuss about cron job. What is a cron job? Runs jobs on a scheduled basis, like a Linux cron. Firstly, what is a Linux cron? Linux cron is a way for you to tell your system that I have a specific task to perform, and this task should be performed at this time. So for example, tasks like I want to take backup at 2 a.m. I want to send this email at 5 p.m. on 15th of January. So things like that can be performed via Linux cron. So let's just quickly see the format for the Linux cron. If I go to my GitHub notes, and what you see here is the way you can express a cron is like this. There are 5 fields, and these fields are, first field is for the minute, then hour, day of the month, and day of the week, and these are your available options. So if I scroll below, I have given few common examples that you would see often used. So here I am saying every minute perform health checks, then every hour at minute 0 hourly database backups or report generation. So I'll let you read through these examples, and I would also like to mention that there is a website called crontab guru, and there are plenty more that you can use to verify that the cron expression that you are using will be doing the task at the specific time that you want it to do. You do not want that you wrote a cron expression and then it triggered at a time that you do not want it to trigger. So always verify your cron expressions using a website like crontab guru. So for example, in my diagrams, what I am saying is run a task every minute. So if I show you the example, if you write something like this, here we are saying run this every 5 minutes. If you have a /1, then that implies run it every minute. So let's go to crontab guru and see whether this expression is correctly formatted. So I'll also add an asterisk here, and then this would be */1, and as we see it is correct, it will run every minute. So that's about cron expressions, and I'll let you read the GitHub notes if you want to understand it further. Then I'll move to the diagrams again. Runs jobs on a scheduled basis. The schedule is decided by the cron expression, and I want you to pay attention here. It says runs jobs, so cron job sits at the top, and then whenever some action is to be performed, a job is created, and then that job, based on the configuration that you have provided, will create the pods. So if I want to put it crisply, a cron job in Kubernetes is used to run tasks on a scheduled basis, and the schedule for that is provided by the cron expression. Cron job controller is just creating a job, and in turn that job is running the pods. So in the jobs section, we discussed that job would run as soon as you apply your YAML, and it will finish the task. Here, as soon as you apply the cron job YAML, there is a schedule associated with it, and as soon as the timings are met with that schedule, then that job is executed. So in summary, at each scheduled time, the cron job controller automatically creates a new job object, and that job is responsible for running one or more pods to complete the task. So if I move to the left, here I have a normal job YAML, and here I have a cron job YAML. If you see in the job YAML, there is a spec section that is defined here. So if I talk about cron jobs, here you have this schedule first, and that is expected because you want it to have a schedule, and then there is a job template, and inside that job template you exactly have the same fields. Hence we can easily conclude that cron job is just providing a schedule, and based on that schedule a job is created. So in this example, cron job has provided a schedule that this job should be running every minute, hence a job will be created every minute. And we have learned in our previous section that TTL seconds after finished will decide what to do once the job has completed, either successfully or have failed. What has to be done? It says that once the job has completed, you remove the job object after 60 seconds. So for in this example, if you do not do that, if you do not have TTL seconds after finished timer, then this cron job would have created so many jobs. In 5 minutes it would have created 5 jobs. So that is how it would work if this timer is not present here. Then rest of the things like completions, parallelism, back off limit, they all behave the same way, because essentially this is a job YAML that is living rent free in the cron job YAML. As simple as that. I'll just quickly give you a one-liner about these. If you have not watched the jobs section and you are here just to see how cron jobs work, completions is the number of pods that will be running to complete your job. I'm saying to complete your job. Being successful or unsuccessful depends on a lot of things. For example, if your application code is not written correctly, then that job will not be finished. Parallelism defines whether to run the pods sequentially or to run them concurrently. Here parallelism is 2, which implies that both these pods defined in the completions section will run concurrently. If completions was 10 and parallelism was 5, then the job would first create 5 pods, and once those 5 pods have completed, then another set of 5 pods would have been created, because the completions was 10 and parallelism was defined as 5. Then there is a back off limit. For example, if a pod is spun, it failed to perform the job. Second time it also failed to perform the job. Third time it also failed, and fourth time it also failed. In that scenario, that pod will be recreated 4 times to give it a chance to complete the job. If it failed 4 times, then the job will be failed. Now the second point is creates job object at specific time based on the schedule we define, and the schedule is defined with the cron expression. Each job then creates pods or pod to complete the task. We all know that. Automatically retries failed job based on backoff policies, and here the backoff limit is defined as 4. Commonly used for recurring tasks like backup. For example, if I want to perform backup of a few files at, let's say, 2 a.m. in the morning, then I can use cron job to perform the same. Second is report generations. Maybe your manager has asked you to give me a report of application 1 at 9 a.m. in the morning. Then you will have cron expression to generate that report, and once that report is generated, you can have it auto delivered to your manager's inbox. Then is system cleanups. Same, if I want to clean temporary files at, let's say, 9 p.m. at night every day, then I can use cron job for this purpose. So when you think about job, think about one-off tasks that you want to do. For example, like we discussed, performing DB migrations, copying file from one place to another, or tasks similar to this. And then cron job, you use them when you have to do something at a scheduled time. Now let's move to Visual Studio Code and do a demo for this. I'll close this job.yaml and I'll open cronjob.yaml. And what you see on screen, this part we have already seen before, and it is only this section that we have added. Rest, pretty much everything is same. Now I'll go to the terminal. I'll run kubectl apply -f cronjob.yaml. Now we have written here that this will run every minute. So if I run kubectl get cj is the short name for cron job, you see that here is a cron job and here is the schedule for it. If I run kubectl get pods, I don't see any pods created yet, because remember, our cron job is scheduled to run every minute. So as soon as 60 seconds pass, you would see the pods are created, and here 2 pods will be created because the completions is 2 and parallelism is also 2, hence 2 pods will be started simultaneously. So if I go here and now run kubectl get pods, I see that 2 pods are running and their age is 11 seconds. And ideally, what you see here is we are just sleeping for 10 seconds and then the task for this container is completed. So if I run kubectl get pods now, I see the completed status. This is 30 seconds here, and once this timer reaches 60 seconds, these pods will be auto removed by the garbage collector, because first the job will be removed. Why the job will be removed? Because after 60 seconds we are saying clean up the job, and once the job is cleaned, then there is a garbage collector in Kubernetes that will also remove the pods. So if I run this command again, I see that previous pods have completed status and they should have been deleted. Let's run this command again to see that, and you see 2 new pods are created. Why these new pods are created? Because this cron job is running every minute. So let's run this again. Oh, and you see now these pods whose status was completed are also deleted. Now if I run kubectl get jobs, then you would see that it is creating a job behind the scenes, and this job was created by the cron job controller. If I run kubectl get cj, you would see my cron job still exists, and the name of the job that is created by cron job starts with the name of the cron job, which also implies this job is related to this specific cron job. Here you are seeing only 1 or 2 jobs, but when you are dealing with a humongous cluster, then you would see it gets pretty daunting. So learn to connect the dots. If you see hello cron job here, then the name of the job would have this as a prefix. Now let's clear our screen, and I hope all these concepts are now clear. And let me see if I want to cover anything else. I don't, but I quickly want to show you one thing. Let's do one thing. Let's remove this timer. Okay, let's remove this timer, and then I will apply this YAML again. Let's delete the previous cron job, kubectl, delete cj, hello cj, and then I'll write kubectl apply -f and cj cronjob.yaml. I'll hit enter and let it do its job. Till that time, I want to show you one more thing. Let's go to the GitHub repository, and here I want to show you one important thing. See, we have been discussing, these are called workload management controllers. We have discussed about deployment, daemon set, job, and cron job. There is one more that we want to discuss, that is stateful sets, and we'll cover that later in this course. But for now, I want you to understand when to use each of these, and you would already be thinking in the right direction if you are following this course from the beginning. When to use deployments when you want to have continuous running tasks. For example, when you are running a web server, APIs, or front-end apps, then for them you would want them to run 24/7. Hence, in that scenario, use deployments with a restart policy of always. And if you have any confusions pertaining to restart policy, go and watch day 22 to have a thorough understanding. Then you have a daemon set. Daemon set we discussed in this section ensures every node in your cluster runs an instance of a pod. Here every node is with an asterisk because will the pod run on the control plane node or not depends on the factors that whether your daemon set has a toleration for the control plane node, and it also depends on whether you are running a managed cluster. In managed cluster, you do not have that much control on the control plane. Then you have job. We know job can be used to perform one-off tasks. And then cron job. Cron job is built on top of job. Cron job provides a schedule, and on that schedule a job will run. If you want to perform something at a schedule every day or weekly or monthly, then you can use cron job for that purpose. I have seen cron job mostly used for backups and report generations like you see here, and even for log rotation. Maybe you want to clean a path every week, so you can use cron for that as well. And let's go back to the terminal again, and here now I want to run kubectl get jobs first, and you see that jobs are now piling. Previously our jobs were getting deleted 60 seconds after it was complete. Here it is complete and it's been here for 100 seconds. So let's run this again, and you see these two jobs are still here. If I run kubectl get pods, you will see that the pods are also here, and you do not want this because this will untidy your cluster. We want everything to be clean and tidy. Hence, it is important that when you're dealing with production environments, you use this TTL seconds after finished timer. I have covered everything I wanted to. That concludes our deep dive into daemon sets, jobs, and cron jobs in Kubernetes. We explored how daemon sets ensure pods run on every node, how job handle one-off batch tasks reliably, and how cron jobs help schedule recurring tasks automatically inside the cluster. In the next section, we'll start with the security section. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.